Section 4.2, we're going to talk about prime and composite numbers, okay? So the first thing we need to talk about is what is meant by the words prime and composite. And we need to be really careful about the word prime because there's a very good chance that at least some of you have some misconceptions about what a prime number is. So let's start there. A prime number, by definition, is any positive integer with exactly two distinct positive divisors. So what does the word distinct mean? Different. It means different. So the reason that the number 2 is a prime number is because it has two distinct positive divisors. What are they? 1 and itself 2. Is the number 1 prime? No, it is not. Why not? Yes, it has exactly one divisor. 1. Okay? So 1 is not prime. Now, it's not composite either because the definition here for composite says any positive integer with more than two distinct positive divisors. So for example, 6. 6 is composite because what numbers are positive divisors of 6? 2 and 3 and 1 and 6. It has 4 divisors. But the number 1 has how many divisors? 1. So the number 1 is neither prime nor composite. Okay? Factorization is any expression of a number in factored form. It doesn't have to be factored down to its simplest components. It just means factored. So for example, if you wanted the factorization for the number 8, you could write that it's 2 times 8. You could also write that it's 2 times 2 times 2. Right? Either of those would be factorized forms for 8. 2 times 4 or 2 times 2 times 2. Two distinct factorizations. They're different. All right? But a prime factorization is unique. There is a factorization containing only prime numbers. So if we want to factor the number 8 into its prime components, it is 2 times 2 times 2, and there isn't anything else we could do. And it's not 2 times 2 times 2 times 1, because 1 is not prime. So prime factorization will never have the number 1 in it, okay? We'll never have the number 1 in it. So we're going to do some examples. And as we do some examples, I'm going to show you different ways of doing prime factorization. You may have used one of these, you may have used both of these, but you've used at least one of them. The most common one that I see students use and that are used in textbooks that are sort of brought to my attention, if you will, is something called a factor tree. So raise your hand if you've seen a factor tree before, or maybe you think you have. Most of you have. So let me show you what a factor tree looks like, and I'll talk about the benefits and sort of the drawbacks of a factor tree. The benefits of a factor tree is that you can look at this number and you can decide any number that divides it, and you can start there. So looking at this number, you might look at this and say 10. 10 divides this, and I know it does because why? Because it ends in 0, of course. So we would divide this by 10, and what would we get if I divide this by 10? 2,366. Now the branches at the end of these branches, the 10 and the 2,366, will continue on as long as we have numbers that are composite. 10 is still composite. How can it break down? 2 and 5. Now, 2 and 5 are prime. So we are done with that part of our diagram. 2,366 is probably not one that you know lots about. I look at that and I'm going to go, yeah, I'm not really sure, but I know it's even. And I know it's even. So that's where I'd go next. And your tree and my tree might not look the same. So you might look at that and decide, oh my goodness, it's also divisible by, and try something different. And that's okay. But I know it's even, so I'm going to divide by 2. And if I divide 2,366 by 2, what do I get? Which is definitely not divisible by 2. So I'm kind of out of luck at that point. So I might try 3. Does this divide by 3? Why not? What do they add up to, Emily? They add up to 13. The digits add up to 13. That's not divisible by 3. So what I'm going to do is I'm going to try something else. Well, I don't need to try anything even. It's not an even number. It's not going to be divisible by any even numbers. So 2's no good, 3's no good, not going to try 4. 5? No good, doesn't end in a 5. How about 7?
Yep.
Yeah, and we don't have any tests for 7, so feel free to grab a calculator to just check it out, but it does divide by 7. 7 times what?
169.
169, which you may recognize. It's 13 squared. And if you don't recognize it, you do the same thing. You try 7 again and it doesn't work. You're skipping all the evens. You try 9, it doesn't work. You try 11, it doesn't work. And eventually you get to 13 and it will. Now, the beautiful thing about factor trees are you have multiple ways of doing them. So that really appeals to our sense of there's not just one way to do mathematics. And I really do like that. I think that's very valuable for you guys and for your students. Because so often math is not taught that way, and it's absolutely not true. There is multiple ways of usually doing anything, usually. The thing that's tricky about this is that you have to be careful not to lose your answers because they're interspersed at different intervals along here, and depending on how neat and tidy you are in your work will depend on how hard it is or easy it is to lose something. Okay? So I'm going to go back and circle the end, that is the prime numbers of every single part of this branch.
My teacher would make us do that like once we got to a prime number.
It's not a bad idea. Not a bad idea. These are my 6 prime factors that I have here. And what we're going to do is we're going to list them in order. The in order part's not necessarily like crucial. It's just a nice tidy way of giving my answer. So what's my smallest prime number? 2. And how many of them are there? 2. So this is 2 squared. What's my next smallest prime number? 5. And I need dots between these because these aren't variables. I don't want my 5 and my 7 next to each other to look like 57, of course. So 7's my next one, and there's one of those. And then I have 13, and it's twice, so it's 13 squared. So this is the prime factorization. And when we get to this point, everybody's must match because there is exactly one prime factorization for every number. It is unique. Yes, Ariel?
Why did we do 2 squared and 13 squared? Because doesn't that make it not prime anymore because you can't divide?
Well, the answer is not prime. It's a composite answer. I mean, it's a composite question, a composite number. 23,660 is composite. What we want is we want the factorization at the end to have only prime numbers in it. So the 2, the 5, the 7, the 13, those are all prime, and it's totally fine that they're squared. You don't have to write 2 as 2. You don't have to write it as 2 squared. You could write 2 times 2. It's just consolidated. It's a cleaner, shorter way of writing it.
Okay.
Let me show you one other way of doing it, and then we'll stop on this problem as our last problem for today. This is great. It's wonderful. It leaves a little bit for my heart to love it because it's got a little bit of structure lacking. You got a little too much freedom for my taste, and if you haven't figured out by now, personally, inside my heart, I'm a little OCD. It's just who I am. Owning up to it's half the battle, right? I know this about myself, and I have to stop myself at home with my children sometimes and realize it's okay if this happens. It's really not absolutely crucial. So let me show you, for the little bit more OCD of you, another way of doing it. We're going to start with our 23,660, and what we're going to do is we're going to divide by the smallest prime number possible. What is the smallest prime number that divides this? 2. And we're going to do our division upside down. Every time I do a division, there will be no remainder, because that's the whole point. I'm dividing by things that go in evenly. So, what is 23,660 divided by 2?
11,830.
Oh, wait. Yeah, 11,000. What was it?
11,830.
11,830. And I do the same thing again. I say, what's the smallest prime number that divides this? And the answer is 2. And I do the division on the outside, the 2. And what does that give me?
5,913.
And I look at that and I say, it is no longer divisible by 2. The next thing I should try is 3, and it won't work. We've already discovered that in the other part of this problem. But if you can use your calculator, you test it, it's going to give you some decimal. You're going to be like, yep, that 3 didn't work. If you look at it and you add all the digits together, you're going to get something that's not divisible by 3 and so forth. So after 3, our next option is 5. And if I divide by 5, what do I get?
1,183.
1,183. Do I need to test 2 and 3 and 5 again? No, because if the previous part of this problem didn't divide by 3, this one's not going to either. Okay? So I'm done with testing by 2s, I'm done with testing by 3s. I look at this and I know automatically 5's not going to work. Yeah? So I move on to 7 and we try, and if we try 7, what do we get? 169. And again, we could try 7 again if we weren't sure. We could try, and it won't work. We can try 11 because that's the next prime number, and we find it doesn't work. And eventually we end up at 13. And I'm done when I get here because I've got a prime number. I don't keep dividing. The thing I like about this is that the answer is right here in order. I don't lose anything. I see my 2's are there beside each other, so I know there's 2 of them. I don't have to look throughout the problem. I see 2 squared. I see a 5. I see a 7, and I see a 13 squared. I'm not going to make you do either of these. You get to pick. But I want you to be aware, because your resources that you use when you teach may or may not sort of include this, and you may have students that need more structure or need less structure, and that just fits them better.